Hello and welcome everybody. Today in calculus, we'll be talking about the area under the curve. Actually, more specifically, the area between curves. Back in chapter 5, the last chapter that we did, we concluded that the FTC number 2 allows you to solve for the area under the curve for any function within the boundaries of a to b. And all you have to do is find the antiderivative and plug in the upper bound and plug in the lower bound, subtract one from the other. So here we're going to start looking at some of the other things that we can possibly do with this integral that we just discovered then. So in this first part right here is more of like an introduction, which is, for the most part, hopefully it's something that is trivial, but nonetheless, we should talk about it just in case, okay? So here, you'll notice that in this first problem, what I would like to do is I want to find the area bounded by y of 1 is equal to x over 2, and also y of 2 is divided by, y of 2 is equal to the square root of 2x. So you'll notice that I have the two equations on the right-hand side, and the area that I'm looking for is the boundary that I shaded in green, or lime in this case, that is in between the two. So if you want, we'll go ahead and call that place R for the time being. I want to find out what is the area of that little region called R. So the first thing we're going to do is we're going to find the intersections of these two curves. Sometimes it's given to you, sometimes it's not. So, just in case they're not given to you, we're going to go ahead and solve for it. So here algebraically you can see underneath, that's what I've basically set up. We take the two equations and set them equal to each other and do a little bit of algebra second year and solve for x in this case. And you'll notice that we have two solutions where x is equal to 0 is 1, and then x is equal to 8 is the other solution. And also, just for the sake of, curiosity, I'm going to go ahead and solve for the y values of each one, so then that way we can get a coordinate. So going back to our graph right here, even though you can kind of see it on the curve, the two intersections are going to be over here, one which is going to be at 8, 0. I'm sorry, not 8, 0. It's going to be 8, 4. And then the other one is going to be the origin, which is going to be 0, 0. Now, can you always solve for the intersections by hand? The answer is no, because sometimes you have a complex equation. But if you can, it'll be nice if you could, okay? All right, now that we have the intersections, let's go ahead and think about how do we apply the integral to all of this. If you want to solve for the area underneath the curve, a single curve, you would just take the integral of that equation and then you set up the boundaries from a to b. Well, here's the same thing, but the way I see it is, well, we're just trying to find that region in between the two curves. So why don't we just take the upper function and then minus the lower function, and that would give us the portion that we actually want. So then that right there is going to be our setup right there. You can see right here we have that setup of the integral of the upper function minus the lower function, and then we put the dx right there to indicate that we are integrating with respect to x. And that dx, again, what that means is we're building partitions that are horizontally like this. So we are building kind of like rectangles going this way. Dx is to indicate the size of the base. So you can see that the thickness right here is with respect to x, and that's the representation of it. So the first part right here, that is going to be kind of like the summation of all of the bases, of all of the heights. And then this right here is to multiply by the base of each of those rectangles. But anyhow, as my setup goes, this is what it should look like then. It's going to be the integral of the upper function, and my upper function looks like it's going to be the curve of the square root of 2x, because that's my upper function, minus the lower function, which in this case is going to be y of 1, so it's going to be x over 2. And then that is going to be my setup then, and then we have dx as we said, and my boundary from left to right, well, that's where the intersections come in. So that is going to be from 0 to 8 then. So if we can solve for this integral right here, then that means that we have the region R for our area then. So let's go ahead and do that right now algebraically just to see what we get. Okay, actually more like calculus wise. So let's go ahead and take the antiderivative then. So if I take the antiderivative of the first part, that is going to be 2x raised to the power of 3/2, because we're using the reverse power rule. Remember, not the derivative, but the antiderivative. Now, normally I would produce a 3/2, but because I'm going backwards, then I'm going to produce a 2/3, which is the reciprocal of what I have. And then also, in addition to that, I'm going to produce a 2 because of the chain rule. And I don't want that 2, so I'm going to go ahead and divide by 2. If you need to do this by u substitution so you can see how that works, you can go ahead and do so. Let u equal to 2x, and then that way you can kind of see where those numbers actually come from. But if you're able to see it like this, I think that's probably best. Then we have minus. Now for the other part, the antiderivative would be x to the squared, because again, we're going backward by the power rule. We have that 1/2, right? That was in the original equation already. And then I'm going to multiply by another 1/2 because of the antiderivative, going backward again with the power rule. And then now we look at the boundary from 0 to 8. So we'll just go ahead and clean this up a little bit before we actually plug everything in. So that's going to give us 1/3 multiplied by 2x raised to the power of 3/2 minus 1/4 times x squared. And now we're going to go ahead and plug in the boundaries of 0 to 8. So we're going to go ahead and plug in 8 first. We'll have 1/3 multiplied by 16 raised to the 3/2 minus 1/4 multiplied by 64. And then that's my upper bound. Minus for the lower bound, well, we kind of lucked out in this case. Looks like it's just going to be 0 minus 0. So finally, if we clean this up even more, 16 raised to the 3/2, you can look at that 16 as 4 squared. And then we have the 1/3 multiply to it. And then we have the 3/2 right there, which we can take care of in a sec. And then 1/4 of 64, that I do believe is equal to 16. So let's see, the square and the 1/2 cancels out. So that's 1/3 multiplied by 4 to the 3rd minus 16. 4 to the 3rd, that is equal to 64. So 64 divided by 3 minus 16. And, for the sake of getting it into a simplified fraction, we're going to go ahead and change that 16 into a 48 over 3. So then if I subtract one from the other, let's see, that is going to be 6, that is going to be 1, and then divided by 3. So your answer looks like it's going to be 16 over 3 then. And that is the exact area under the curve then. So that is the area of R. Now, for this integrating thing, for this integral thing, we can actually look at it using a different perspective. Because what if I did not build my partitions horizontally stacked like this from left to right? In this case, you can see how the partitions are actually built. But what if I built it vertically like this? What if I built the stacks vertically, just like in this case right here? Okay, so you'll notice that we can still get the job done. But now I'm saying that my thickness of these rectangles, well, first of all, they're stacked vertically. So then that means the thickness is going to be dy. Okay. Now, in terms of how do you solve for the area, it is exactly the same way. It is going to be your upper function minus your lower function. But your orientation is a little bit different because remember, y is going to be your variable. Y is going to be your kind of like the independent variable in this case. So what I'm trying to say is you're going to have to kind of tilt your head by 90 degrees. And if you can see it, then what's going to happen is this line right here, that is going to be your upper function. Whereas this curve right here, that is going to be your lower function. And again, remember, you can see this if you rotate your head to the right by 90 degrees then. Okay. So if I were to set this up, how will this integral actually looks like? Well, let's see then. So first off, we said that it's going to be dy, meaning that we're integrating with respect to y instead of to x. So what that means is, first of all, if I think about boundaries, it's no longer from 0 to 8, but rather it's from 0 to 4 because we're going from bottom to top. Okay, we're not going from left to right, we're going from the bottom to the top. Now, my upper function is going to be the line, right? And earlier we denoted the line y of 1 is equal to as x over 2. Well, since I need to solve for it in terms of dy, then what I need to do is I need to multiply 2 to the other side. So then that means that we have 2y is equal to x. Remember, your variables are swapped. X becomes y becomes x, kind of like the inverse. So that is going to be my upper function right there. So 2y. And similarly for the other equation, which is y of 2 is equal to the square root of 2x I'm going to go ahead and solve for x just like I did in the other equation. So first I'm going to square both sides. So y squared is equal to 2 over, times x. And then finally, y squared divided by 2 is equal to x. And now that is going to be my lower function then. Okay, so there it is. And let me go ahead and change that because it's supposed to be y squared divided by 2. So what that means is if I take this integral and I solve for it using, just antiderivative, I should get the exact same answer as what I did before. Well, let's just check just to make sure everything is okay then. So let me go ahead and take the antiderivative. 2y, the antiderivative is y squared. And then minus the antiderivative of y squared divided by 2, that is going to be y cubed, and then I'm going to produce a 1/3, so I do believe that this is going to be 1/6 then. Again, boundary is from 0 to 4. So finally, we're going to go ahead and plug in everything. So first of all, that's going to be 16, minus, for the other part, that's going to be 1/6 multiplied by 4 to the third power. So the lower bound, that is going to be equal to 0. So, just writing it out so I'm not skipping any steps. So that's my upper and then that's my lower. And you'll notice that this definitely does look familiar. So that's going to give us 48 over 3, which is the 16 that I'm replacing it with. And then the other part is going to be, 64 divided by 3, right? Oh no, 64 divided by 6. So if I clean that up a little bit, so 48 over 3 minus 32 over 3. So that is going to give us 16 over 3. And there you go, 16 over 3 like we said, okay? Whew, fortunately, I didn't embarrass myself and got the wrong answer. Okay, all right, but there you go. So that basically means now that you have an option of doing the area between curves using dy or dx. And the question is, well, which one do you actually do? And that really all depends on the setup or your orientation. So it all depends on the problem. So here, let's look at this next one right here that you can figure out. Hopefully, you can kind of see as to like what is it that you need to solve for. Find the area of the region, which we call R in this case, and let's think about, tactic-wise as to like how we're going to set this up. If I were to solve for it by using dx, then that means that my partitions are going to be built horizontally. So that means that it looks something like this, right? From left to right, and those are going to be my partitions. My problem with that is that you're going to have to set up two integrals, because if you look at the upper bound and the lower bound, from 0 to 1 right here, you'll notice the upper function is y is equal to x, and then minus the lower function, which is going to be x squared over 4. So that's going to be the first part, from 0 to 1 of dx right there. And that I need to split up, because now from looking at 1 to 2, what I need to do there is I need to set up a different integral, because my upper bound is no longer the function y is equal to x, but rather it's the function 1. So 1 minus x squared divided by 4, and then dx, and then boundary from 1 to 2. So that's what my dx looks like. It's kind of nasty looking because, you have two different integrals that you need to solve for. You can get the job done, but I definitely feel like it's going to be a lot shorter if you, there's definitely a shorter route. So now let's consider what happens if I use dy, where your partitions are basically stacked horizontally, stacked vertically like this. If I do it this way, where everything is vertical, and again, the best way to see it is you need to tilt your head to the right by 90 degrees. If you do so, then it's very clear as to what's the upper bound, what is the lower bound, and you don't even have to split it into two parts. Here, let me just kind of draw some illustrations over here on the right-hand side as to what those partitions looks like. So here's one piece, here's another piece, here's another piece, and so on and so on. And again, if you rotate your head to the right by 90 degrees, you can clearly see then what is the upper function and what is the lower function. So I do believe here we can go ahead and set up then. Let's go ahead and use dy like we said. So the area of R is going to be, my boundaries vertically is going to be from 0 to 1, because this is the lower bound right here, which is y is equal to 0, all the way to the upper bound over here, which is y is equal to 1. Now, the upper function, again, if you rotate your head to the right, then you can see it's from the equation y is equal to x squared over 4. So what I need to do is I need to take that equation and solve for x then. So 4y is equal to x squared. And then afterwards, take the square root of both sides. So square root of 2, actually not square root of 2, it's going to be just 2 times the square root of y is equal to x then. Okay, now technically, yes, you're right. You're supposed to have plus or minus 2 times the square root of y. But if I take the negative of it, that wouldn't make any sense because we're in quadrant 1. So everything is supposed to be positive. So that's going to be my equation. So it's going to be 2 times the square root of y minus the lower function, which is just y is equal to x. Well, then that means it's just plain old y. I definitely would want to integrate this equation right here versus the integral that I set up earlier for x then. Okay, so let's go ahead and finish this off and solve for this. Let's see. I'm going to go ahead and take the antiderivative. So 2 times the square root of y, the antiderivative is y raised to the power of 3/2 multiplied by 2/3, and then the 2 carries over. Then we have minus 1/2 times y squared, boundary from 0 to 1. Plug in the upper bound minus the lower bound. So that's 4/3 multiplied by 1 minus 1/2 times 1. All of that is the upper minus the lower, which is 0 minus 0. Okay, so finally we clean up as much as we can. So it looks like it's 4/3 minus 1/2. So that is going to give us 8/6 minus what is it here? 3/6? Yes, 3/6. I can't do basic math anymore. So it's going to be 5/6 then. And that's going to be the area under the area of R then. Okay. All right. Now let's go ahead and look at this final example where everything is going to be calculator based because, you know, not all the equations can be solved by hand. So the idea here is, you know, still the same thing. What I want to do is I want to find the area bounded by the function y of 1, which is equal to x times x6 minus x, and then y of 2, which is going to be cosine of x. Now over here on the right hand side, I have graphed it out for you. Actually, I used decimals to graph it out for you. The red curve is the y of 1, that parabola, whereas y of 2 is going to be cosine of x, which is going to be blue. You can see what I did was I basically set up on the graphing calculator where each one is, you know, its own respective equation, y of 1 and y of 2. And you can do exactly the same thing also on your graphing calculator. In addition to that, I also used the graphing calculator ahead of time to figure out what are the intersections of the two curves, which are located right here on the bottom. So if you remember, you're supposed to use that intersect key, and that's how I found the boundaries then. Remember, now that you know that you can use dx or dy, it'll be ideal to solve for the entire coordinate rather than just the x values or rather than just the y values. Okay, so let's think about how are we going to solve for this then? Do I want to use dy or dx? If I use dx, you can see that the partitions are just going to be stacked horizontally. So here you can see that if I do it this way with using dx, I think that's probably ideal because you can see the upper function minus the lower function just perfectly, right, from left to right. But whereas if I were to use dy, then that might not be a good idea because here you can see that my stacks right here, my upper function and my lower function, well, that's going to be just problematic because my upper and lower function seems like it's the same equation. And then once you get to the bottom, well, we don't even want to think about what's going to happen there. So basically, once again, the conclusion is let's go ahead and use dx. So here it is. Now, this is something that you can also do on the AP test, in which I really recommend. What I'm going to say is now that we know that we're going to use dx, I'm going to go ahead and look at the x, right, boundaries on the left and the x boundary on the right. I'm going to go ahead and say more specifically, let a be equal to that number that's on the left and b be that number that's on the right because, you know, those are not exactly nice numbers. So it'll be easier if I just set them as variables. Then what I need to solve for, according to what we have, is that I need to solve for the integral from a to b of y of 1 minus y of 2 dx. If you set that up right there, that gives you most of the credit. And now all you have to do is just use your calculator to find out what is the numerical area under the curve. So that is going to be a job for the calculator, which you don't have to solve for by hand. Remember, there are a lot of equations where you cannot actually solve the antiderivative. So that's where your calculator comes in, because you need to use it to solve for the area on the curve. So the way we're going to do that is something called finite integration, okay? So again, at this point, once you set up the integral, you can use the calculator to solve for via FNIT, which means finite integration. And this finite integration function is right below the numerical derivative function, which you have learned from the first, I think like the third chapter or something like that. So anyhow, in the older model of your calculator, what you would do is you would select the finite integration key, and it'll take you back to the main screen, and this is what you have to put in there: finite integration, and then open parentheses, y's of 2 minus y's of 1, because remember, y's of 2 and y's of 1 are basically these equations right here, so you don't have to put them in, but if you want to put it in instead, that's fine, okay? Comma, x, and then comma, then your lower bound, comma, your upper bound. So those guys, if you want, you can technically put in a and b so long as you define what a and b are in your calculator. This x is to indicate that the variable that you're taking the derivative with respect to, the integral with respect to. And then the first part is going to be your boundaries then. And then these two right here, well, that's your lower bound, and then that's your upper bound. Okay, so lower, upper, okay, and then this is going to be your variable, and then these are going to be my boundary. So that's basically what this means then for finite integration. Put all that into your calculator, and then you should be able to see your answer then. In the newer model, if you put the finite integration key, you literally see an integral sign, which is nice, because then you can just go ahead and plug in accordingly. Put in 0.169 on the bottom, or a if you want. Put in b on top, which is 5.845. In the function, you can put y1 minus y2, or if you want, for those of you guys that just want to write it out, you can go ahead and say x multiplied by 6 minus x minus the cosine of x. Either one of those will be okay. And the last part over here, now this is the part that you have to be careful, because on your calculator, when you put the finite integration key, that d right here, you're going to actually be missing something over here, and you're going to have to put in yourself x. Because sometimes you might want to integrate with respect to, like, say, a different variable. So you have to tell the calculator what you want. Nonetheless, if you put that in, then this is the numerical answer that you're supposed to get, which is 36.438. And remember, just like always, you're always going to have to round it off to 3 decimal places. All right, so that is definitely a mouthful. So take some time to look this over. Thank you so much for watching, and I will see you next time. Take care.